Hi, everyone. I'm Chris Sommers from Keysight Technologies. Today's talk will be given by Georgios Nikolaidis, software architect, and Petr Kastovsky, product marketing, both from Intel. They're going to talk about combining the Intel Tofino Intelligent Fabric processor with Intel FPGAs and memory to obtain new heights in performance and scale. I've been involved in system designs myself where these techniques were considered, so I'm really excited to see their work. Take it away, gentlemen.
Hello, everyone, and thank you, Chris, for the introduction. As the name of the session suggests, we will talk about an architecture for multi-terabit programmable networking functions. So let's start with the programmability aspect first. In the past, but even today, there are fixed function networking devices used throughout the networks. These devices are designed by chip architects, and their feature set is a result of the design choices made by these architects. What we've seen in the past is that the evolution of networks has been faster than the traditional chip design lifecycle, and the network owners and operators have been looking into ways of taking control of their network's design. The software-defined network design all the way down to the data plane packet processing is what fulfills their needs. It is the new age of programmable ASIC. And in this age, it is up to the networking software developers to define what features and functions will their network provide. It is these software developers who define what networking protocols are going to be supported and how the chip resources are going to be allocated for particular functions. That, for example, allows them to achieve unique scale parameters by allocating all the chip resources to a particular feature, but also to extend the lifetime of the device in the network by allowing updates and upgrades in the field. Intel Tofino Intelligent Fabric Processor, or IFP, is a fully programmable switch chip that has been designed to address the traditional switching use cases like spine, leaf, or top-of-rack switching. However, as the networking community got exposed to its programmability, we've seen an explosion in the number of various networking applications and use cases. Some of these include different types of gateways, either cloud or telco gateways. In the case of cloud gateways, the typical functions include tunnel terminations and translations, load balancing, as well as security functions like DDoS detection and mitigation. In case of the telco gateways, like Broadband Network Gateway or BNG, it is of essence to guarantee service level agreements and allocated bandwidth that customers are paying for, as well as to provide very accurate traffic statistics for billing and charging for each customer. In many of these use cases, there is not only a need for high bandwidth and flexibility, which is well addressed by Tofino, but there's also a need for extra large session scale or even functions that are not typically available in a data center focused switch ASIC. So let's take a look at a use case presented in a paper by Alibaba team during the last year's SIGCOMM conference. Alibaba has been facing a dramatic increase in network traffic during the shopping festivals that can easily draw millions of shopper visits, leading to terabits per second of data traffic. The scale and growth rate of Alibaba Cloud make horizontal scaling unsustainable for the following reasons. First is the cost of buying high number of systems and then maintaining these large deployments, managing them, as well as troubleshooting them. Second reason is that the per core performance growth is slower than the growth of the speed of elephant flows, or also called heavy hitter flows in the network, which can lead to oversubscription and requires additional headroom when sizing the systems, which again further drives the costs. These challenges can be addressed by deploying a switch-based solution that is typically capable of handling multiple terabits of network traffic per single system. But while the switch-based solution deals with the throughput scale issue, it creates a state scale issue, as today's switch ASICs come with an on-chip memory that can store tables with, let's say, millions of entries, which is perfectly fine for the traditional switching applications. However, for applications like cloud gateways, the requirements are on the order of hundreds of millions of entries. In order to address this state or session scale requirement, we leverage the Tofino expanded architecture that complements Tofino switch chip with Intel FPGAs to enable 2 orders of magnitude increase in table and buffer capacity, as well as possibility to add new types of functions. Today, we see 2 significant groups of use cases using the FPGA's expansions to either provide extra large table or extra large buffer. The extra large tables are typically needed in applications that require hundreds of millions of table entries. These applications include the previously mentioned cloud gateways, as well as some of telco applications that are listed here: carrier grade, network address translation, network packet brokers, and so on. The extra large buffers are typically needed in telco gateway use cases, where there's a need to do advanced shaping and scheduling functions with the buffers. The Tofino expanded architecture is a system-level architecture that combines existing chips, and there are different ways how these systems can be implemented. To provide some examples, let's take a look at the Keysight architecture, where the Tofino switch chip provides all the front panel connectivity, and it's up to the code running in the Tofino to make a decision whether part of the network traffic would be forwarded for additional processing in the FPGAs. Another implementation is an inline architecture, where part of the network-facing ports is connected to the Tofino, and part is connected to the FPGAs, so that the traffic flowing from one part of the network to another needs to pass both Tofino and FPGAs. There are various pros and cons of these implementations, and the choice is typically use case dependent. Similarly to different implementations, there are also different hardware form factors. So far, we've identified 3 different form factors, where the first one is a combination of an existing off-the-shelf Tofino-based switch device and off-the-shelf FPGA-based card. This is a very flexible form factor, allowing for arbitrary connections between Tofino and FPGAs using just the optical cables. The downside is that we need a server to host the FPGA cards. The second option is an integrated platform that we call server switch, combining CPUs, FPGAs, and Tofino into a single rack-mountable system. The internal architecture is predefined, so the system needs to be selected according to the use case requirements. And then the last option is a chassis-based platform, where different sleds or blades can be used to achieve different ratios of compute, networking, and storage. Going forward, we will consider the server switch form factor that we've used to develop an application that we will describe and also demonstrate in the rest of this session. The application in mind is layer 4 server load balancing. Server load balancing is an essential data center service that is responsible for efficient utilization of data center resources. And as was indicated earlier in the presentation, a horizontal scaling has its limits and becomes cost prohibitive at terabit network traffic speed. So in order to keep the costs under control, we've developed stateful server load balancing acceleration, which is leveraging the Tofino and FPGA chips to provide both high throughput as well as high session scale. The hardware platform that we're using offers 3.2 terabits of network bandwidth and supports 256 million sessions. So how does it work? The standard scale-out approach is based on load balancing running in software. So whenever a request comes from the client, it goes to software load balancer that makes the load balancing decision and forwards the packet to the right backend server, which then delivers the content to the client. In order to improve performance of the load balancing operation, we introduce session cache that runs on the server switch with Tofino and FPGAs inside. At the beginning of a session, the packet processing flow is pretty similar to the standard approach. Client sends a request, which is forwarded to the software load balancer that makes the load balancing decision and forwards the packet to the right backend server. The load balancing decision is also stored in the session cache of the accelerator so that following packets of the same session can be forwarded to the right backend server directly by the accelerator. That leads to significantly reduced load on the software load balancers and makes the load balancing service more efficient, allowing to deploy more backend servers and thus generate more revenue. Now let's take a closer look at how it works in the load balancing accelerator. What we can see here is the server switch system, which has multiple modules: CPU module, switch module, and FPGA module. The CPU module runs the control plane that is based on Sonic network operating system. We are reusing existing Sonic features and adding load balancing specific capabilities. The Tofino sitting on the switch module does most of the data plane processing and packet forwarding. And then we've got FPGAs, one or more FPGAs in the FPGA module, providing the session table expansion. The data plane diagram is simplified to capture the key load balancing operations, leaving out features like SYN flood detection and mitigation that will be presented later on in the session. How does the life of a session look like here? So when the first packet of a session comes in case of a TCP session based on a SYN flag, we are able to forward the packet directly to the control plane. As we know, this is a new session and we don't have an entry for that. The control plane makes the load balancing decision and stores the decision in the accelerator so that the next packet of the same session, when it comes in, the data plane can make the forwarding decision itself. As we can see in the diagram, we've got a concept of the hot and warm cache, where the hot cache in Tofino takes care of the most active sessions and the FPGA provides the required session scale. So first, the lookup happens in the hot cache, and if there is a hit, packet gets forwarded to the right backend server. If there's a miss, a lookup request is created and sent to one of the FPGAs, where another lookup is done in much larger tables. And this lookup can again have two results, hit or miss. In the case of a hit, Tofino uses the lookup result to forward the packet to the right destination. In case of a miss, we don't have any rule for this particular session, and the packet gets forwarded to the control plane. That concludes the life cycle of the session. And now let me hand it over to Georgios, who will show us the demo.
So today I will show you a demo of our software load balancer accelerator appliance. In this demo, I'm going to show you a client that is launching several requests towards a backend server. All these requests will need to be load balanced. So they will first need to go to a load balancer that runs IPVS. There are going to be 2 runs in this demo. In the first run, we have the SLBA functionality turned off. So every packet that starts from the client will need to go to the software load balancer. The software load balancer is going to look up where that packet needs to go, and it's going to forward it to its intended backend server. As you can see in the graphs at the top, every packet that comes in is classified as a miss for both our Tofino and our FPGA cache. If you take a look at the backend server, you can see that it consumes throughput in order to service all these requests. This is TCP traffic. We're using HyperV, and you can see that it utilizes a good amount of its CPU in order to serve all these requests. The software load balancer exhibits a similar behavior because it needs to do the load balancing operation. So we can see that it consumes a good amount of throughput and a good amount of its bandwidth when it has traffic flowing in. In the second iteration in this demo, we're going to show what happens when we turn on the software load balancing acceleration function. So the workload in this case is the exact same one as in the first run. We have HyperV sessions that are more and more HyperV sessions, in total 1,000 of these sessions that are launched progressively. And as you can see on the backend server, things look pretty much identical as in the first run. If you notice over here, you're going to see though that most of the packets are now classified as hits in our FPGA cache. There are small spikes of packets that are misses, and these are just the first packets of every flow. Over here, you can see that there are multiple new flows that are detected and added to our FPGA cache. But you will notice that a big difference we have a very big difference in the outcome on our software load balancer. So both the throughput and the CPU utilization are essentially in the idle state. This is because the software load balancer only needs to be involved during the first packet of each flow, but after that, it doesn't really have to do anything else. This means that this leads to all the savings and the acceleration of the load balancing function that we are after. We have also added a security module to our SLBA appliance. And in this demo, I'm going to show you mitigation of a SYN-FLOOD attack. SYN-FLOOD attacks are quite widespread. SYN-FLOOD is a very typical type of attack that involves attackers sending SYN packets towards a service. The concept behind the attack is that whenever a server receives a TCP SYN, it needs to allocate a bunch of memory in order to save all the state that will be necessary in order to serve the TCP connection. Of course, if we have several of these of these TCP SYNs coming in, we will have to allocate a lot of memory space, and at some point, the available memory space is going to be exhausted. At that point, every new request will have to be denied, hence a denial of service attack. In the scenario that we have over here, we have about 8,000 legitimate HTTP requests launched by clients, and we also have about 6,000 TCP SYNs sent per second by our attacker. The attacker is basically sending these requests in waves, hence you can see the on and off pattern. At this stage, the security module is not turned on. So in the graph over here, you can see the number of TCP SYNs that we observe in our SLBA appliance. And basically every new SYN seems identical, whether it's coming from a legitimate client or not. At this moment, we are turning on our security module, and you will see that now we classify our TCP SYNs into 2 classes. The class on the top is our normal legitimate traffic, but the one on the bottom is the unauthenticated traffic, our attacker's traffic. The the moment that we classify a TCP SYN as coming from an attacker, we don't forward that to our backend server, hence protecting the valuable resources over there. We achieve that using a method called SYN cookie, which is a challenge response method that does not consume any resources on our SLBA appliance. This means that this sort of protection to our network comes at a very low cost, and it is very scalable. Thank you.
Yes.
Okay, thanks a lot. Those graphs really made it easy to see the benefits of your approach, and really this compelling case here. And I'm sure there's a lot of other use cases that will benefit equally. By the way, what was the graphing tool you used? It looks like a custom application.
It's our custom front end. Yeah,
it's nice because it's very real time as opposed to something like Prometheus and Grafana, which is a little bit slower update rate. So
exactly,
really good.
Yeah,
really good. So different questions come to mind. What were some of the challenges in partitioning and implementing that design?
So one of the challenges is that we are building an appliance that has to deal with multiple functionalities. So in our case, we are providing a full forwarding pipeline that is controlled with Sonic. And at the same time, we are accelerating a network function. This means that we need to be very careful about the way that we use our resources in order to make the device fully functional as a switch, but at the same time provide all the added benefit of the accelerated network function. And all that while having to deal with essentially 3 different appliances: a CPU, Tofino, and an FPGA. So making this whole thing work seamlessly takes a good amount of engineering.
I'll bet. When you had these extensions to the P4 pipeline done, let's say outside of the switching ASIC, how did you expose or connect those to the data plane? Was it just through ports and sort of the design was the designer knows how the design works, and so you sort of stitch the pieces together in your head, or was there some integration with the P4 code, like through externs or something a little more intimate?
So our approach is the former that you mentioned. We consider the latter. The challenge that we have currently is that when you are concealing all this functionality, it's harder to optimize and squeeze out every last bit of resource. Usually these optimizations these abstractions end up wasting a little bit of resource. So in our effort to try and maximize the resource utilization, we opted for keeping a design that is based essentially on a pipeline on the Tofino side that's unaware of the functionality that happens in the FPGA and handling everything on the platform level.
I see. There's other talks in this P4 workshop that integrate FPGAs and P4 as well. And for example, there's a SmartNIC use case. And I'm wondering, there's probably going to be a lot of this because people are always trying to add scale, add features very cleverly. And FPGAs are a known tool for always extending things, customizing. Do you think the P4 community should step back and say, this is a way of life? Maybe the architecture, the tooling, the language itself should somehow embrace this extensibility? Or is that a holy grail?
You could say that's a holy grail. I think it is definitely something that we need to aspire to, and something that we at Intel are also working towards. We are very interested in architectures that involve multiple types of devices, and a lot of our efforts are towards making it as seamless as possible for the application developer to use all these different devices in a way that can maximize the benefit and make them achieve their business goals.
Yeah. I would, if I may, I would add to that specifically for FPGAs, They sit between, the world of ASIC, which has very, hardware-like performance, and software which is like fully programmable. And they need to, they offer a lot of benefits, but they also need to deal with the challenges of sort of both worlds. And so I guess the system architects should choose carefully what to do where in order to, leverage the resources efficiently. Otherwise, you could start, building some very complex algorithms in places where you don't really want them. So that is something to keep in mind.
Yeah, I guess as a pure software developer, it would be nice to just say, well, it's a cost benefits trade-off. I can use these blocks of hardware or this other blocks of hardware, and I get to choose. Instead, it's kind of like you have to be a bit of a genius to find the optimum solution at any point in the technology timeline. It'd be nice if someone came up with a unified field theory to make all this easier for pure software developers. I'll leave that up to you guys.
Thank you.
Sort of a related question. Do you think the hardware implementations that we have, like switching ASICs or smart NICs, DPUs, IPUs, do you think there's an opportunity to design them so that they can be extended off chip with FPGAs or something, maybe using a coherent interface, something other than, Ethernet ports, so that it's a little more intimately tied into the pipeline, and maybe taking it one step further, even allowing for chiplet designs that allow you to say, well, I want more TCAN, I'm willing to pay for it. Intel, make me 10,000 of these. Do you think that's conceivable?
I believe so. I believe that's a future, with everything being, in the same package for performance, power, space reasons. I'm sure we'll see these things happen in the future.
Cool. One last easy question. What platform did you implement those designs on?
So the platform that was used in this particular demo is called CAR 5056, and it's a system built by Caswell, which is a Taiwanese system vendor.
Oh, great. I remember seeing the product announcements some time back. Well, great. This was a lot of fun. And, as a Tofino developer myself, I'd love to play with all this stuff in my spare time. Hopefully I'll get the chance someday. Thank you very much for the fascinating talk, and keep up the great work.
Thank you,
Chris.